Hi everyone, Krishna this side, and in this particular video, I'll be covering this LeetCode problem 894, all possible full binary trees. We have given an integer n, so we need to return a list of all possible full binary trees with n nodes. Each node of each tree in the answer must have node.val equals to 0. Each element of the answer in the root node of one possible tree. Okay. Yeah. So you may return the final list of trees in any order. A full binary tree in the binary tree where each node has exactly 0 or 2 children. Okay. So if we look into this problem statement, so we need to create all possible full binary trees, and we need to return that list. Okay. So if we look here, a full binary tree is going to have exactly 0 or 2 children. So okay. So if n equals to 3, definitely the root node is been there, and left and right children are there. Okay, so only one possible binary tree that we can have, that is full binary tree, and that is something what we need to return in form of list. Okay, so if we look into this particular example, if n equals to 7, right? So here in the left side we have only one uh, children, and it is not having any left or right children. Okay, so in this particular example, here in the left side one children is there, and in right side we have all the different possible full binary trees, right? So here in the right side, in the first, for the first node, it has exactly two children. For this one it has exactly true, and this one it is not having any one, right? So it has 0 children. Okay, so in the next example, what we can do is we can remove these two childrens, and we can add it to this particular one here in this way, right? In the next example, what we can do is we can take this one and we can put it for this left side of them, right? And next example, what we can do is even we can take this one and we can add it to this one of the children that we have in the left side, or we can take that and add it to this left side of this particular left side of the tree. Okay, so yes, these are different possible trees, and that is something what we need to return in form of list. Okay, so yes, how to solve this particular problem, right? So let us think it, right? So here in the constraint, if we look, n is actually realized from 1 to 20. So if number is even, n is actually even, let us suppose n equals to 2, is it even possible to form binary tree? Just think through it, right? So the root node is going to be there, and whatever the extra remaining children that we have, even if we put in the left side, it is not going to fulfill what exactly the full binary tree means, right? Because it should have exactly 0 or 2 children, right? So if we add it to the left side, definitely in the right side we don't have any children, or even if we put it into the right side, of course we don't have any children in the left side, right? So exactly it has only one children in any form. So obviously it is not been what we are actually looking at, right? So it is not forming a full binary tree, so of course we need to return empty list. So what we will do is, for first, let's create a list here, and sorry, and we'll check that if n is actually even number, right? So we can directly try to modulo with 2, and if it is getting 0 as a reminder, then definitely it is actually even number. So what we can do is we can return this simple list, right? So that's the first condition that we can have. What else, right? So if n equals to 1, in that particular case, whatever the object we create, let us suppose I create this tree node as a root new tree node. It has 0. Yes, if we look here, it is saying that node.val equals to 0. And even if we look into this definition of this binary tree, it has val, and it holds left and right tree node, and three constructor, default constructor, and in the first constructor it accepts the value. That is what I am passing. Even if we do not pass it, by default it is going to hold 0 as a value, so it doesn't matter if I put 0 or not. Okay, so yes, what I'll do is, as in we are require the answer in form of list. So whatever the list I have created, I'll put this particular tree node into that list. List dot add this root, and simply what we can do is we can return this one, right? So return this list. Okay. So if n equals to 1, that condition also is satisfied here. Now what if n equals to 3? for 2, 4, 6, 8, all those get satisfied here itself because we are just returning empty list. But when n equals to 3, in that condition, what we can try is, so if we look for n equals to 3, obviously only one left child is there and one right child is there, right? So yes, what I'll try to think is, what if n equals to 5 now? In n equals to 3, I can simply create a tree node for left child. I can simply create tree node for the right child with this type of objects, and I can create a root node in which I'll put this left and right, and I'll put that particular into the list and I can return it. But what if n equals to 5? In that case, we will be having different combinations, right? So one combination, possible combination is see 1, 2, 3, 4, 5. So just do not consider these left out elements. In that way, if we look here, so we can either put in the left side one children, and in the right side remaining whatever the children that we have, we can put that, and that is going to be one formation, right? So just ignore these two nodes. So this is going to be one binary tree that we can have, full binary tree. And next example, what we can do is, we can take this both and we can put it in this side. So in that way, right side will be having one, and in the left side, how many children we put? We actually put three children, right? So yes, that is another formation that we can have. Apart from that, is there any another possibility that we can think of? No, right? So actually, we can have two different possibilities. Okay. So yes, what I can do is, then in that case, I'll try to get in the left side. First, we have only one node. In the right side, remaining nodes, whatever we have in the bucket, those all nodes we need to dump it into the right side. In next example, what I can try is, I can try to increase few nodes in the left side, and I can reduce whatever the extra nodes that I added to the left side. Those nodes I can reduce it from the right side, correct? So that is something what I need to think of, right? So what I'll do is, in the recursive way, I'll explain this particular part. Okay, tree node, I'll get this from this particular same function only in the recursive way. What I'll get, left tree, left left list, I'll say it like that. Okay, and all possible fbt, and here let us suppose if n equals to 3, in that condition I can pass only one, right? Because in the left side only one single element is going to be there, one single node is going to be there. So in right side, even for the right side list, I'll get, okay, right lst all possible fbt. Here in that case also, one is what we need to pass, right? So if we look here, this is what I am getting it for n equals to n equals to 3. In that condition only I am trying to get this particular example. Okay, I am just trying to put these values and trying to get the list of these nodes. As in, when I call this function recursively, it goes here n equals to 1, and it comes here and it returns a list, right, which is having an object, and basically it returns a list. And this is something what this particular list is been added into the left side. Okay, and once this job is done, now what happens again, it try to recursively go and check whether if sorry, it is basically returning the list, right? Now it comes here, the function call comes here. Now here it checks n equals to 1, again it recursive calls, and again this right side right list also we get it from this particular function. Okay, both these lists we have now. Okay, now what I can try to do is, I can have a root node. So I'll create a root node to which I'll put all the different combination if at all possibly happened, right? If at all we got different combinations. For now, we are just getting only single combinations, right? In the left side, only one node is there. In the right side, only one node is there. So that is the single combination that we have when n equals to 3, and that is what we will be adding it to the left side. So in the root node, okay. So what I'll do is, in a case of if we get different combinations, list of different tree nodes, okay. Right now, as I said, we are just passing 1 and 1 because we have only n equals to 3, and for that, for the root node, we will be only have left children and right children, and from there I am getting the list of this tree nodes, right? So basically only one tree node is what we are getting. But in a case if there are different combinations that we will be having, right? So let us suppose n equals to 7. In that case, in the left side only one node is there, but in the right side we have this particular list, we have this particular list, and we have this particular sorry, in this this is not falling into the one, right? So it is falling when n equals to 3 is what we pass to the left side. In the right side it is actually, this is what a formation that we have. When n equals to 5 is what we pass to the left side, right? In the right side we are just having only one remaining element. So these like different combinations that we have, right? So that is what we need to form here. And for n equals to 3, only one node is what we are passing it, right? So in case if n equals to 5 is there, so one I passed, one is root node, and remaining whatever we have, what are the remaining elements that we have? Two nodes we are already having from the left side and from the tree node, root node. Whatever the remaining what we have, 3 is something what we have remaining, right? So whatever the remaining list nodes we get, tree nodes, that is something what I am trying to pass to the right side. Okay, so we need to try out different combinations right now. So currently I just thought of like, okay, n equals to 1, that is for left side I am just having holding only one children node. In the right side I am holding 3 children node. Okay, so that is for this combination that is feasible. But what if I want n equals to 3 here and n equals to 1 here in the right side? This is also another possible combinations, right? So for that, like what we can try is we will run a for loop for I equals to 1, I less than n, and I, what we will do is I'll jump it with two decimals, right? Because there is no option that if we try for even numbers it will simply return empty list. So we will directly jump to the n equals to 3, and that is 3 elements we will be holding in the left side, and whatever the remaining elements that we have, that we will add it to the right side of the tree node, and we will get the list. Okay, so what I will do is I'll just create a for loop. Inside the for loop I'll put this particular piece of code, and first, in first example, I'll pass I as a 1 in the left side. So I'll consider only one single element is there in the left side. And in that case, in the right side, what is the remaining element? N minus I minus 1. Because one root node is there, to which these left trees, whatever the different combinations that we got from this particular recursive function, right? Those all different possible functions, different possible tree nodes that we will be holding in this particular list. Okay, in the right side we will have another different list of tree nodes, those possible combinations that we got. So what we will do is we will go through all of them, and we will get the exact tree root node from all those possible combinations. Okay, so tree node, left node from this left LST for okay, I already created this tree node, right node from right LST. Okay, so see, you guys may get confused with these two different for loops now. See, I guess you guys got this idea, right? Like I first tried only with if n equals to 3. In that case, I can pass only one nodes here. But what if n equals to 5? In that case, I can have different combinations, right? In the left side, I can have one element, or I can have here, if you look, I can have 5 elements, or I can have 3 elements. So all these different possible combinations that we have, we can hold all of them in this particular list. Okay. So if n equals to 1, in the left side it has only one possible combination. Okay, it has only one possible combination. But for the right side, what we are passing is whatever the remaining that we have. So remaining 5 is that we will get. So here we will pass 5. So in that 5, for the 5 it has different type of combinations, right? This is one combination, this is another combination. So all those list we will get it right over here. Okay, now it is having only one uh, tree node, but this has two tree nodes. Okay, two different combinations that we got. With n equals to 1 we pass, and n equals to 5 here we pass, we get these different combinations. Now what we do is all those combinations now we can add them. So for the here with this n equals to 1, we can have these two different for loops. So in the left node we have only one as a combination that we got from the left side, but from the right side we got two different combinations. So those, all those two different combinations should register with this particular one, right? So for this root node I can have one, that is fine, but from the right side we have two different possibilities, right? So those needs to be considered to this particular root node. So what I can do is I create a root node, that is something what I'll create inside this one, because each time we will be having a root node, and for this root node I will be adding this left node to this root dot, or what we can do is we can simply pass 0 comma. If we look into this constructor, they are saying simply we can put the left and right of the tree node. So I'll put here left node and right node. Okay, so now this particular one gives me two combinations when n equals to 5, but this particular one gives me only one combination. So all those possible combinations needs to be added to this particular row. Okay, now these two has been done. Now this for loop again runs. I'll get incremented to 3. Here we pass 3 as all possible combinations into this FET. So this again rerun, and it try to get all the different combinations and it add it, return it into this particular list of tree node. Okay, and then again here whatever the remaining elements that are we have, those we will add. So if I equals to 3 here we pass, here also it will pass 3, and both of these gives us all different combinations. Now in this particular example this gives us only one possible combination, because if n equals to 3, definitely we will be having only one possible combination. Each has the root node has been a left side and a right side, right? So this gives us one possible combination, this gives us one possible combinations, and we loop through that particular list, and we create another root node to which we add these left side combination, right side combinations. Okay, and simply what we can do is we will add this into the list dot add this root, and at the end what we can do is once we add it, we will, once this for loop is also done, we will return this list. Okay, so the moment we add it, if there is only one possible combinations that we have, just consider that n equals to 3. So here it doesn't fall. Now here we come, n equals to 1 is something what we pass here, and remaining value if we calculate here, it also 1 is what we get. From the left this function will call and we get a list. From right this function will call, this returns a list. Both will be having a single tree node into this list. So this list we again loop through them. If there are multiple possible combinations that we can have possibly, we will run them into this for loop, and we create a root to which we add all, if there are multiple possible combinations, all those root tree node we create and we add it into the list. Once this loop is done, we come here and we return the list. Okay, this is like a simplest form of code that we can write in the recursive manner. And even if we look now for the 7, right? So first it pass as 1, here it pass as 5. Okay, 5 or whatever the remaining value that I am talking about. And this recursive function first call, it come here and it return a list to this one. For the right, again it goes here and it checks n equals to 5. Again it come here, again it loops to the this particular function. It generate all different possible combinations into the stack, and it generate this list, and ultimately it try to come back, the callback will return all those lists, and this right list will be having all those formations, and we loop through them and we ultimately return the list. Okay, this is how we can recursively write down this particular form of code. Now if we try to run this particular code, okay, so if I run this, okay, unknown error, I don't know what is trying to say. Okay, let me just try to connect it to my personal, I don't know, is some problem with the internet. Till then just look into this particular code, right? So yes, we need in the left side we might have different combinations, right? So ideally we can have 1 or 3, or here if we look here we pass 5, right? So in the right side definitely remaining whatever the element that we can have, those elements we can pass and we can get the list out of it. Okay, and the moment we get that, we will be adding it to the root node, and we once we add it to the root node we will return that list. Okay, once we add it. So yes, recursively, I mean, you can try all root recursive form of tree like structures, and then you guys will get that idea what we are trying to do here. If still you didn't get it, and let me run it. And if we think about here, right? So okay, uh, what is possibly is it okay? Yeah, this should get closed. I just need to. All right, this needs to be kept outside, and let's just move this part of code a bit inside so we can run it. Yeah, it is getting accepted, but the problem is if we think about the solution, right, this particular recursive solution, we are trying to recompute a particular solution again and again. Let us suppose if n equals to 5 is there, this 5 can generate same kind of tree. Even this particular tree we can utilize it in the left side as well, right? Correct. And this particular, if n equals to 3, the same structure we can have in the left side as well. So this is kind of like repetition of same kind of structure, and we are trying to compute them again and again. For that, what we can do is we can try to memorize this particular tree like structures, and we can use the DP here. So what I can do is I'll use a hash map here. In the hash map, if this particular integer is actually this, if n equals to 5, let us suppose, if that has been actually computed already. If not, we can hold that value into this hash map. And again, if we are trying to recompute the same solution, if n equals to 5 is what we pass and we try to get all the possible full binary trees, we can get it from the hash map. So in the hash map, we will simply store all these lists, because this particular solution will go in factorial, uh, and that is something what we don't want to have, right? So sorry, it will go in exponential, right? Because we will try to generate all these different combinations again and again. So it goes like we are running this for loop twice again. And yes, this outer for loop, like, it's like it goes in exponential completely. So what we will do is we'll create a hash map, and in the hash map the first condition that we check is if the hash map, the map dot contains key, if n, whatever the n we have here, if in the hash map we have that particular list of tree node, then we can simply return that. If it contains, then simply return map dot get that for that particular integer n, we just return that list. Okay, that is the base condition that we add it for any DP type of problems in the recursive solutions. And what else? Once the root list is created outside here, I'll put it simply map dot put, because ultimately the whatever the stack gets created in the recursive call, so that stack it returns back to the previous function, and this map will hold that particular information. Okay, so whatever the n we have here in that particular callback, that for that n I'll put the list. Okay, so again, if at any point in time, whenever the list gets generated for a solution, that we can utilize it in the left side, because that is what we are trying to do is, right? First we pass here 1, here we pass it 5 for n equals to 7, then we pass 3, here we pass 3 for 3, whatever the solution we computed, the hash map will hold that list. So again, for right side, when it try to generate it, it check if it is having the hash map, so it simply get that value. So whatever the list, both the list we have, we can simply compute them. And next time here we pass it 5, here we pass 1. Now for 5 we already generated from the right side for with n equals to 1 when we pass it for the left side, right? So what are those possible combinations we have, the map will simply return it, and we simply can have them. And we can generate the for loop, and we generate the root node, and we return it. Okay, so that's what we will do it from this particular example. With this one, we can actually reduce the complexity from this exponential to at least it goes to like 4 to the power of n divided by some root n, something like that. It comes down, because tn is what we are running it from n times, and these exponential keep on going, and uh, but there will be break because the memorization is what we are using. So obviously it at least come to the power of n, near around to the power of n. Okay, n into 2 to the power of n. So that's what we get it. The memory is also sorry, this space complexity is also same, because all different possible combinations we are actually storing it into the map, right? So yeah, this way we can at least reduce it from the exponential to the power of n, near to that one. Okay, so that's all from this particular example. I'm not sure if you guys get it without pen and paper. I get it really difficult to explain, but I don't have that setup to explain you guys on pen and paper. But hopefully, if you guys ask, or if you guys think that I can try it out with that particular setups, I'll do my best and I'll get the setups, and we'll try to consider that. Okay. Yes, that's all from my side. Yeah, thank you for watching this video. Bye bye.